we get started? So it's my pleasure to introduce the second candidate for the astronomy and astrophysics faculty position, Dr. Gregory Snyder. Dr. Snyder went to undergraduate at Princeton University and then went on to his PhD at Harvard. And he finished his PhD in 2013. After doing that, he moved to the Space Telescope Sciences Institute in Baltimore, Maryland, that runs the Hubble Space Telescope and the James Webb, and will run the James Webb Space Telescope when it launches. He then was there for 2 years as a postdoc, and then became a Giacconi Fellow at the same institution and has been there as a Giacconi Fellow since 2015. Dr. Snyder works on, recently at least, on the modeling side of galaxy evolution. He started working on star formation in distant galaxy clusters and in distant galaxy clusters, but in recent years has really worked a lot on trying to understand how we can observe models of galaxy evolution, computational models, and kind of compare them directly to observations. I'm sure he's going to tell us a lot about that today. Yeah, he's very well known for this kind of work. And so it's my pleasure to say welcome. And yeah.
Thank you, Greg. So I'm really excited to be here today to tell you all about some recent work I've done uniting surveys and simulations to explore galaxy evolution. And so in a nutshell, my research philosophy is to combine telescope data with cosmological simulations of galaxy formation to tell the stories of galaxy assembly. And in my talk today, I'm hopefully will explain what I mean by all that. And I wanted to start just by outlining one of the major questions in the field of galaxy formation, and that is, how do we form galaxies of different types? And so I'm showing here on the slide a star-forming blue spiral galaxy on the left, much like our own Milky Way galaxy, and a non-star-forming redder elliptical type galaxy on the right. And so one of the things we want to understand is why these two classes of galaxies and other classes of galaxies came to be in the universe. And so in my talk today, I'm going to give an overview of the field of galaxy formation, a little bit more detail than I just did. I'm going to talk about the physics of galaxies, how we simulate those physics, and how we can test those simulations with observations. And I'll describe in detail my approach for this problem, which is to create and investigate synthetic observations of galaxy formation simulations. Then I'll talk about some science results. The first one will be that simulations form galaxies with realistic morphologies, or shapes. And then mock surveys reconcile some puzzling data about distant galaxies. And then finally, I'll wrap up with, I think, an exciting path forward for galaxy formation studies, and that is to use simulations as a basis for training machine learning classifiers to understand galaxy mergers and other processes in the formation of galaxies. So why should you care about galaxies? Well, we all live in a galaxy called the Milky Way galaxy. So here's an image of the Milky Way galaxy in the night sky. Galaxies are composed of stars, as well as gas and dust in between stars, as well as dark matter. And the way I think about galaxies, there are basically two things, and why I find them interesting. They're gravitationally bound collections of stars and their remnants, gas and dust and dark matter. And they're really a bridge from the large-scale cosmology of the universe we live in and the cosmic origins of humans as a species. And so all of the processes that happen inside galaxies where we live are things like star formation and planet formation and the recycling and mixing of metals and things that eventually went and formed all the matter in this room, all the objects in this room. A term that I'm going to be using a couple times throughout the introduction of this talk is called a dark matter halo. And so for the purposes of this talk, a dark matter halo is the bound region where a galaxy forms and evolves. And so here I'm showing a rendering from a cosmological simulation of a Milky Way type galaxy, where the region in which the gravitationally bound matter affects things is quite large compared to the scales of the Milky Way galaxy. And so the entire Milky Way galaxy that I showed on the slide before would fit inside the central regions of this dark matter halo. Now, these dark matter halos and galaxies inside them grow in the large-scale structures that are set by the early universe fluctuations. And so on the left, I'm showing a map of the early universe fluctuations measured by the ESA Planck satellite. This is an all-sky map showing extremely tiny fluctuations in the matter and energy density fields in the early universe. And these tiny fluctuations grow under the force of gravity to be the structures of dark matter and galaxies that we see today. And so on the right, I'm showing just an example of that from a cosmological simulation where we're seeing the distribution of dark matter halos in the early universe and then again in the later universe, where I've highlighted here in the bottom a tiny point of light, which would be the Milky Way, the entire Milky Way halo that I showed on the slide before, would fit within this cosmic web structure of cosmic structure formation. And so the point I want you to take away from this slide is that at any point in this structure, it's possible that different physical processes are dominating the formation of Milky Way galaxies, or galaxies of mass like the Milky Way galaxy. In particular, galaxies will have different tidal fields, different torques from gravity that they experience as they form and evolve along cosmic webs like this one. And one of the things we need to understand the different types of galaxies is this exact process. A few specific quantitative parameters about galaxies. So in my talk today, I'll be focusing on massive galaxies. And by massive galaxies, I mean galaxies that contain 10 to the 11 solar masses of gas plus stars. They contain 10 to 20 times more matter than that in dark matter. They're about 10,000 to 100,000 light years across from edge to edge. And they're diverse. So there's many different types of galaxies. I showed 2 on the first slide. But galaxies come in different shapes and sizes, different features that we can measure. And yet those features aren't just random. Those features correlate with the assembly of those galaxies and with the physical processes that are acting inside the galaxies. And so we can hope to understand, by studying the diversity of galaxies that we see in the universe in addition to our Milky Way, we can hope to understand something about the physics that drove them to look the way they do. So the field of galaxy formation boils down to understanding why and how galaxies of different types formed. One of the major tools we've had for understanding this process are simulations. And so on this slide, I'm going to show a dark matter only simulation. So we're only looking at the process of gravity in the early universe, from the early universe to today. And so I'll start the movie. And it starts from very tiny fluctuations, as I mentioned, in the early universe, that grow under the force of gravity into the very first dark matter halos. So these very brilliant points of light here are not actually what we would observe, but these are dark matter density peaks that we're observing we're seeing in the simulation. However, we could never actually detect this in any instrumentation that we have today. This is simply the backbone of the structure of the dark matter halos that are forming a galaxy that's roughly the mass of the Milky Way. And that leads me to my next point, which is that at the end of this time evolution, there'll be a dark matter halo in the center, roughly the size for the Milky Way. But this single dark matter halo actually grew from the collection of tens of thousands or millions of smaller dark matter halos that grew to become the Milky Way galaxy, or the dark matter halo for the Milky Way galaxy. And so this process we call merging. Merging of dark matter halos, or the merging of galaxies that reside in dark matter halos, is a fundamental topic in the field of galaxy formation that I'll be spending a lot of time on later in the talk. But what I wanted to point out is that the process of the merging of dark matter halos is very difficult to detect. You can't observe this process directly. And so we can use the galaxies that populate the dark matter halos, especially in the early universe, to understand the process of assembly, this merging of smaller galaxies into bigger galaxies as they progress in their lives. And so observing galaxies is one way to get the dark matter properties in the early universe. One of the key challenges that we face when modeling galaxies in this way is that the dark matter evolves according to gravity. Relatively easy to calculate the force of gravity, even in big volumes, even at high spatial detail. But it's much more difficult to calculate how the gas evolves. And the gas evolves very differently from the dark matter. And so you can't just use n-body simulations or similar techniques to evolve the forces that are acting on galaxies, like these that have been observed with the Hubble Space Telescope. And so see, there's 2 galaxies showing many of the different processes that are important for the assembly of galaxies beyond just the gravitational physics. And I've highlighted a few of them on this slide. One of them is star formation. And then star formation causes stars to form and evolve. And those evolved stars launch winds from their dying remnants and energetic outflows that then change how the gas would then evolve. And so this is what, in astronomers' terms, we call feedback. This is a feedback loop where galaxies form stars. Those stars emit energy that then changes how the future evolution of star formation would occur inside the galaxy. Similarly, there's the formation of supermassive black holes, which we think reside in the centers of all massive galaxies. And they have similar physics, where they will accrete matter and launch energetic winds into their nearby regions, which then can alter how galaxies would be observed, rather than just simple dark matter and even simple gas physics. There's the large-scale gas flows, which evolve largely according to the equations of hydrodynamics, possibly including magnetic fields and other processes. And there's galaxy mergers, which can take all of these components of galaxies, including the dark matter, mash them together, mix them up, and then change the subsequent evolution of those components. And so the state of the art is to co-evolve the dark matter and gas in simulations. And so I'm showing here a movie of the Illustrious Project, which I'll be talking about more in my talk today. This is a collaboration of which I've been a major part to understand this co-evolution between dark matter and gas in galaxies. And so this movie is going to start showing the dark matter distribution, similar to the renderings I've been showing before. But it's then going to change after a few seconds, 30 seconds or so, into showing the gas temperature distribution. And so this is showing the structure of galaxies. Each of these bright points of light is just the rendering of the dark matter density. And inside each of those points will be a forming galaxy. Now it switches over to the gas temperature slowly. And so you change from blue to red. And we see all the other important processes going on in the formation of galaxies in the simulation. A few of those are highlighted. The flashing lights, if you can see the little flickering lights in all of the individual galaxies, are supernova explosions that are affecting the gas around those explosions in important ways. And the bigger plumes of red smoke that you see coming out of the larger galaxies is black hole winds. So this is energy being deposited into the regions around galaxies from the supermassive black holes at their centers. And so this way of looking at a state-of-the-art cosmological simulation is a way to highlight those important processes and how they are relevant for changing the distribution of gas around galaxies. Question?
I thought that those little clumps with galaxies, the explosions look large compared to galactic.
That's exactly right. And so one of the really important challenges in this work is that the scales at which star formation and supernova feedback and black holes act are sort of parsec scales inside of galaxies. These are things the size of the solar system or the solar group area. It's tiny regions of galaxies. However, their radiation can be emitted across the entire scale of a dark matter halo or even larger. And so these processes can then push those gas around on those scales and then have a really important coupling between the tiniest scales inside of galaxies and the largest scales outside of galaxies. And so it's really important that we study this to try and get a handle on what's going on there, but it's also really challenging work. The other major tool we have at our disposal, in many ways the only tool for a century or more centuries of astronomy, is observations. And so here I'm showing how observations can measure the outcomes of these chaotic processes that I've just described. This is showing a tiny slice of an observation made by the Hubble Space Telescope called the Hubble Ultra Deep Field. This is a small region of a bigger footprint that was about 1/100th the size of the full moon. And so Hubble observed it for several weeks in different colors of light. And so we can then put together pictures of these galaxies as they're observed here in the real universe and see that there are thousands of galaxies in this image. Many of those galaxies have different types. They have different tidal arms, spiral arms. They have double nuclei. They have clumps. They have different colors. They have different shapes and sizes. And so there's really a huge diversity of different galaxies that we can observe through observations like this one. And then those things can be used as the original and the main input into understanding how these processes act in galaxies. Of course, this technique has a challenge. And one of the primary challenges is that it's very difficult to, say, identify three galaxies in observation space and understand how they're related to each other. And so that's one reason we turn to models. And so in these three galaxies, I'm showing a tiny, very distant galaxy. And so when we make observations like this one, we see galaxies all the way back to the very first few billion years in the universe. And so this might be one example of those galaxies here. But in our theory of galaxy formation, we want to understand, will that galaxy grow to look like this galaxy, which might be a blue spiral galaxy, so kind of like the Milky Way, or turn into this red elliptical galaxy like this one? And just by observing individual distinct points of light from galaxies, we can't know for sure how that happens. We can't sit around for billions of years and watch how this galaxy then turns into that galaxy directly. And so we have to use models to sort of interpolate between these observations that we make. However, observations have been extremely useful for putting galaxies in the proper context, at least as a function of time. And so this is a diagram showing the evolution of galaxies as they are related to the Big Bang and the evolution of the universe since the Big Bang. And so we now know that the universe is about 14 billion years old. Galaxies grew out of smaller pieces in the early in the sort of dark ages to the first stars and first galaxies. And then this era of galaxy development is where I spend most of my time working. And so we're able to say how distant a galaxy is, roughly speaking. And so we can put galaxies into bins and classify them in different ways using observations. And we've had a lot of great success doing that and getting galaxies at least into the proper order and the proper relationship to each other in observations without knowing the causal evolution of their growth. And so I want to end with just a quick primer on observations and distances in galaxy formation. And so here I'm showing two examples. So the universe is expanding, and that stretching of space-time causes the light from galaxies to be shifted in wavelength. And in astronomy, we could call that redshift, typically because galaxies are usually so far away that they're all receding from us in the expansion of the universe. And so on the left, I'm showing an example of what I'm calling a low redshift galaxy. And for the purposes of my talk, that means things going on recently in galaxies less far away. And really in the last few billion years, last 1 to 5 or 10 billion years of the universe is what I mean by low redshift in this talk. And so I'm showing here a nice picture from the Hubble Ultra Deep Field of a low redshift galaxy. I want to contrast that with a high redshift galaxy, a galaxy in the more distant universe. And so this should be thought of as happening a long time ago in a galaxy far, far away. For the purposes of this talk, that's about the first 6 billion years of evolution in the universe. And fundamentally, they are dimmer, smaller, and have stretched wavelengths compared to the observations of low redshift galaxies. And the striking difference is that we have thousands of bits of information about this galaxy on the left, the low redshift galaxy, whereas we only have a few bits of information about the high redshift galaxy. All of this structure that we can observe in low redshift galaxies is shrunken into the size of a telescope resolution element on the high redshift galaxies. And so we lose the ability to track as much detail in the high redshift universe than we do in the low redshift universe. So to summarize the basic toolbox that we'll be using to understand galaxies, simulations predict the positions and velocities for stars, gas, and dark matter as a function of time throughout the entire 14 billion year history of the universe in principle. And observations provide electromagnetic signals of distinct and real galaxies and their components. And so these two tools have their weaknesses and their strengths. I've described a few of them. The strengths of the simulations is that we can evolve things as a function of time and relate them to our observations in different ways. The observations have the strength of actually being real galaxies. And so the simulations, we never will know if we actually have the right model for galaxy formation. Or it may take us a long time to understand whether we have the right model for galaxy formation, whereas observations are concrete and they actually measure real physics. And so that's one of the things that I like to work on in my work, is taking the strengths of both of these and combining them. And so in particular, I view the strength of observations as having the ability to constrain models of galaxy formation and other physics. And the strength of simulations is really to help interpret data. And so we can use the results of simulations to get a better understanding of how galaxies assembled. And this was alluded to in an earlier question. One of the key challenges in doing this work is that the energy emitted by stars, gas, dust, and from near black holes couples atomic scale physics to cosmological ones. And so for the reasons I mentioned before, all of these processes will drive radiation and momentum and energy around inside of galaxies and on scales even bigger than galaxies. And so that is an extremely multi-scale problem. And so computationally, it's very expensive and very difficult. And in fact, we don't even necessarily know the right equations to use for these processes. And so we have to iterate many times to understand how those equations work. And so what folks discovered early on when trying this game is that if you ignore this coupling, you get very wrong answers. And so this is a plot showing the number of galaxies as a function of the mass that forms in stars. And the real observations are the data points as the black squares. They're shown along this hooked curve in the middle of the plot. And if you just put in the simplest gas cooling and star formation physics, ignoring the radiative coupling that I mentioned earlier, you get a line that tracks the number density of dark matter halos, which happens to have a very straight line through this region here. And so that's what this black curve is showing here. And so if you ignore that coupling, you get a very incorrect answer for the production of galaxies in your simulation. And so for a couple decades now, scientists have been working to alleviate this problem by modeling galaxy formation in different ways and by inserting equations that happen to reflect these important processes. On the left, I'm showing a way to do it in a cartoon fashion from a dark matter only simulation, where you're only modeling the force of gravity using your computer. And then inside the region of influence of a dark matter halo, you might evolve a set of partial differential equations that would relate to how the galaxy would grow and evolve according to all of these important processes. And so those have been around for a couple decades now, and they're still a really important part of our framework for understanding galaxies. But what I'm going to be talking about today are so-called hydrodynamic simulations of cosmological galaxy formation. And they're shown on the right. Here, the gas is allowed to cool and evolve under the equations of hydrodynamics inside the region of the dark matter halo. Once that gas cools inside the galaxy, that's where we put our unknown physics. So we allow the computer to evolve how the gas evolves on somewhat larger scales. And then all of the important unknowns about the radiative coupling between star formation, black holes, and the resulting evolution of galaxies gets put into the center of galaxies in different ways. And so for a few decades now, this can be summarized as scientists panicking about their model for star formation and supernova feedback, or worrying about their model for black hole growth and feedback onto the galaxies. And then what has been unknown until recently is just how these processes then can take gas and particles and metals and things from inside galaxies all the way to the outsides of galaxies. And so it's an important computational challenge to tune all of these three components, or to understand how to build a model of all three of these components in a simulation, but people did the work. And so people spent many years of their lives working towards iterating on this basic framework. And so what they've discovered is that the basic requirements are inputting winds driven by supernovae and supermassive black holes. And so on the left, I'm showing the influence of supernovae, where these are the explosive end results of star formation, where the gas is driven out of halos. And so this energy input has the effect of reducing the amount of stars that form in low-mass galaxies. And similarly, in high-mass galaxies, supermassive black holes can grow in a fashion that's proportional to the dark matter halo mass. And so then, once they have enough mass, they can inject energy and then prevent the formation of stars in higher mass dark matter halos, shown on the right. And all of our modern models of galaxy formation, many of our modern models of galaxy formation actually now fit pretty close to the data. And so this is showing 6 examples of both dark matter only and hydrodynamic simulations of galaxy formation physics that reproduce roughly this basic challenge.
Question.
Yeah.
You told us that you weren't sure what equations or parameters to use. So has that just been fit from that guesswork and?
It's been fit, but using a framework of things that seem reasonable. But yes, so there are still some free parameters that have been fit to the data.
How many free parameters?
I think nowadays it's around 6. But it depends exactly how you count, and I think people would disagree over that number.
Pretty hard to miss a curve like that with 6 parameters.
I agree. So once we've had these now at least frameworks for modeling the physics of galaxy formation, there are still many questions. And so the questions that I've been most interested in answering, and the one that I'll focus on most in this talk, is how do galaxies get their stars and gas? What is the role of galaxy mergers? So that's a subset of the first question. However, in my future work, I'm really interested in exactly this question, actually, is whether other physical processes can explain these trends. And I think the observations are still unclear on the question of whether supermassive black holes actually can change how galaxies grow and evolve. And so I think there's still some degeneracy in the availability of other models that could explain the high mass end of galaxy formation. And so that's a really interesting question for the future. So the tools that I've spent the last few years working with, I call big cosmological hydrodynamic simulations. These are simulations that simulate a cubic volume of about 1/3 of a billion light years on a side. They use comprehensive physics models to simulate about 10,000 massive galaxies. And they're achieving resolution elements, so the detail that they can resolve inside of galaxies is about 1,000 light years. And so that's something like 10 to 100 times or 1,000 times smaller than the size of the galaxy. And so we can actually start to resolve individual pieces of galaxies in these large volumes. Each of them costs about 50 million CPU hours, roughly speaking. And so that's a big investment of the community's time and effort. And roughly speaking, that translates into $1 to $10 million in electricity costs, depending on when it's run and where it's run, and so on. And so it's actually quite important that we get the most out of these simulations in order to learn the most we can about how galaxies form and evolve. And so I believe that they offer fairly unique platforms to study the origins of galaxy populations. The project that I've been involved in the most is called the Illustrious Project, which got started in 2014 and the years prior. There's a couple of papers that initiated the project by Mark Vogelsberger, Shai Ganel, and Deborah Siachki, 2014 and 2015. But since that time, the Illustrious Project has led directly to over 120 publications in the literature. The team published our public data through an advanced programming interface, so you can go and actually download the data now if you wanted to from this website. And so this has been a really, I think, neat opportunity to get everyone in astronomy involved in analyzing these simulations. And the thing that got me most interested in analyzing this simulation is that there's a really strong case to take the outputs of these simulations and directly predict our data for major telescopes. So rather than just show you a rendering of the dark matter process or showing the gas physics in the movie that I showed, we can actually go all the way to the frame that we observe in our telescopes, like the Hubble Space Telescope, the light, the photons that we observe from these galaxies, and study them and learn things about galaxies. And so I think this has been pretty successful. There have been a handful of mock observation studies that I've had the privilege of leading and collaborating on. To support some of this work, we obtained a Hubble Space Telescope theory grant with me as the PI and a National Science Foundation grant with me as the co-PI, simply to make these mock observations and analyze them and understand the results of the simulation better, as well as our observations. And one of the nice things we've done recently is post some examples of our mock observations and tools for understanding those mock observations on the Mikulski Archive for Space Telescopes at the Space Telescope Science Institute. And so some of our mock observations are downloadable from the Illustrious Project or from Space Telescope directly, depending on which perspective you find the most useful. And so once you have your simulation, your simulated data, I figured we could go and look at the galaxies. And so I wanted to know what the galaxies looked like. And so here's one galaxy of the 10,000 or so galaxies that the Illustrious Project formed. And I know what you're thinking. That looks nothing like the galaxies you showed me before, Greg. That has, this doesn't look anything like the galaxies you showed me. And that's because what I'm showing here is not how the galaxy is observed to our telescopes, but how it looks to our computer. So this is showing 500,000 individual points. These are discrete star cluster models from one galaxy that formed in the Illustrious simulation, and we have tens of thousands of examples like this one, where I've rendered the star distribution, which is a function of position, velocity, mass, and time on which the star is formed, as a function of 2D position on the slide. And a third dimension I've added to this particular slide is the formation time of when those stars formed in the universe. And so the dark purple points that you can see are stars that formed recently. And the light yellow or orangish points are stars that formed later in the universe. And so you can actually see some important elements of galaxy assembly actually in this distribution. There's a bright clump of young stars at the bottom, sort of at 6 o'clock in this image. There's a plume of young stars off to the left. I'm not exactly sure what could cause that, possibly the disruption of a smaller galaxy through a merger or some other process, as well as a stream or 2 or 3 streams of young stars that almost certainly came from the disruption of a galaxy satellite that fell into this dark matter halo and was disrupted as it passed through. And so then we can go take the next step and convert those star models into stellar light. And that takes 4 steps, generally speaking. We need to use population models for the stars that form as a function of time, which produces the emission of light from those model regions. We need to assume something about the intervening cosmic dust, which I showed you in the Milky Way galaxy at the beginning of the talk. We need to project it into 2D space. And we need to apply some wavelength filter. So we're only looking at a specific wavelength of light. Here is a near infrared wavelength, as might be observed in some telescopes. And so now we can actually relate between the model and the stellar light pretty directly. We see this bright clump on the bottom. This is the young clump of stars that I showed you earlier. And there's the plume off to the right, which is the disrupted satellite galaxy, which is observed in this purple plume here. And so we can actually, in principle, use stellar light to understand these complicated processes of how galaxies came to be assembled. The challenge, of course, is that that's not the only step. And we need to take another couple of steps to get to the point of what our telescopes actually observe. And so on the next slide, I'm showing mock Hubble data for the same system. And so I'll flip back and forth a few times. And you can see that we lose a lot of information. And so the steps we've taken in doing this transformation is then to add to our 4 steps distance dimming, aperture limited resolution, pixelization, and sky shot noise, which are the 4 most important elements of converting to data that looks like it would be taken off of our telescopes and applied it to our stellar light image. And we lose information about that stream that I showed you. We lose a lot of the faint features in the outskirts of galaxies, yet we retain some key information about the galaxy. We understand that there's 2 bright clumps in the middle, so this is possibly the merger of 2 more massive galaxies that formed early in the universe, and so we can tell that just simply from the Hubble data, even though it's of poor quality than the ideal universe. And there's this other bright clump that I showed you from the beginning, which also is still detectable in this particular mock observation. And so then we can now directly relate the simulated universe to the mock observed universe using steps like this one. And the first question I had for our team was, do comprehensive simulations like the Illustrious Project produce the correct galaxy morphologies? So this is showing a plot of data, real galaxies, as a function of star formation rate and their mass in stars. So the y-axis is the star formation rate, the rate at which they're currently assembling new stars inside them, and the total mass in stars as they're observed on the x-axis. And the color of each of these bins is described by the morphology or shape of the galaxy, where generally speaking, we go from spiral galaxies in the black and blue points to elliptical galaxies in the red points. And what we can see from a plot like this one is that elliptical galaxies live in regions of high mass in stars, and relatively low star formation rate. So they're not forming new stars at a very significant pace. And so we wanted to understand whether our simulations actually reflect this critical observation about galaxies. To do that, we used a set of synthetic images that we used from our HST grant, or that we used our HST grant to support the creation of. And so we start with the stars, the stellar field in a bunch of galaxies, as I'm showing here. This is just a similar rendering to the first one I showed for 12 example galaxies from Illustrious. We then apply our 8 steps to go to mock observations in all of these time bins and galaxies. And so there's really tens of thousands more examples that we actually analyzed than I'm showing here. And so we apply these 8 steps, as well as 2 other steps. One is to actually analyze the emission of light from these mock images, and so analyze the structures that we observe in the light profiles, and to analyze the results, and to look at the trends. And so we looked at a plot like this, the star formation rate versus mass in stars, and yes, we're achieving in a model like Illustrious comprehensive or correct galaxy morphologies as a function of these parameters. And so what I'm plotting here is the quantitative morphology, as published in a paper in 2015, showing the evolution from spiral to elliptical galaxies. And yes, the basic trend is in place. We have forming galaxies at different star formation rates and different masses that occur, or eventually will have, or in the late stages of the universe, have the right shapes and structures and morphologies of galaxies as observed in our simulated images. And so I view this as an important success in the field of computational cosmology. It's taken us several decades to get to this point when people originally wanted to simulate galaxies. And so I think we're now at a point where simulations form galaxies with realistic morphologies. And Illustrious is not the only one where this is the case, but there are many competing and collaborating simulations which achieve this as well. Do you have a question, Greg?
Yeah, one of the things that's hard to tell from this is about the relative fractions of ellipticals and spirals.
Yeah.
I mean, I can't really tell it from the color coding. So do you get the right proportionality between different types as a function of mass?
And so one of the challenges, one of the problems with the Illustrious model is that there wasn't enough cessation of star formation in this sort of intermediate mass. And so actually you can kind of see there's like a shark bite out of the distribution here. It's a little subtle in this image. But I still think that it's important that if we're getting the assembly of star formation and matter in galaxies that occupy the right regions of space, they end up having the right shape. And so we may not be populating this region of space correctly, but for the galaxies that do occupy that region, they have the same morphologies, roughly speaking, as they would in the real universe.
Do they land in the Tully-Fisher relation too?
Yeah. Yeah. And so this is a really important first step for the rest of my talk. And so for the rest of my talk, I'm going to be talking about using simulations to interpret data. And it's really important that we start with at least something that looks like the real universe and looks like galaxies that have the right properties and scaling relations of galaxies, at least to first order from our simulations. And so I'm going to be using the result, this fact to go ahead and learn more about the real universe. And so for the rest of my talk, I'm going to be focusing on what's called the merger hypothesis. And this was a theory put forward in the 1970s that the collision of spiral galaxies forms the population of elliptical galaxies. And for a long time now, people have known that mergers of galaxies are important for the assembly of the dark matter halos of those galaxies because of the movie that I showed earlier. In addition, they can scramble the stellar fields of the galaxies. And so if you have a nice, thin, star-forming spiral galaxy, you can sort of heat up those stars and make them look like an elliptical galaxy would. And so that was a natural explanation for the formation of elliptical galaxies. However, today I would say that mergers are viewed as being potentially much more broad in their impact. And so we don't know if this exact statement is correct. The mergers of spirals produce the population of ellipticals, and probably it's too simplistic. But mergers are possibly also extremely important for building the supermassive black holes at the centers of galaxies. So mergers can drive extreme gravitational torques, which drive gas into the centers of galaxies more efficiently than galaxies alone. And so you can have mergers that are actually crucial for building the massive black holes that we observe in galaxies. And mergers might also be crucial for distributing gas. And so I talked about how these processes can push gas out into the outside regions of galaxies, and those gas reservoirs are potentially available from mergers. And so the gas evolution, which is not even shown on a slide like this one, is something that's potentially extremely important for the future evolution of the galaxies. And so on this slide, I'm showing a sequence of galaxy merger stages from 1 to 6. These are just real galaxies observed with the Hubble Space Telescope in some sort of order. So galaxies start as a close pair of galaxies. They move together, they interact gravitationally and otherwise, and they eventually merge together to form the final remnant. And in the first section of the merger portion of my talk, I'm going to be talking about galaxies that haven't yet merged. And so these are galaxies that are nearby to each other. They're probably gravitationally interacting or will be very soon and will likely be a final merger in the near future. And so I want to know, do we know how often mergers happen? And so we can observe the numbers of mergers and calculate the fractions of mergers, but that doesn't translate naturally into the rate of mergers and in particular a physical rate for understanding how important they are in understanding galaxies. And so then we're working towards how do mergers transform galaxies in the future. So a nice fact about galaxy mergers is that they're a natural result of this cosmological structure formation process. And we have simulations, including Illustrious, work led by Vicente Rodriguez-Gomez et al. In 2015, which predict the galaxy merger rate as a function of time that we would observe in our data, or which we measure in our simulations. And that prediction is very simple. It depends exactly on what you call a galaxy merger, what mass galaxy you consider. But our cold dark matter, lambda cold dark matter universe typically predicts a galaxy merger rate that is low, very low at the present time, so time 0, redshift 0, and very high in the early time. And so the galaxy merger rate is evolving steeply as a function of time over the 14 billion years of the universe. But otherwise, it's quite simple. And so it's potentially easy to understand. Observers have done a phenomenal job coming to agreement that in the last 10 billion years or so, observations agree with this prediction. So down here in the first corner of the plot, I have a check mark because people have generally agreed that at least the direction and magnitude of the evolution in the galaxy merger rate evolves roughly as it's predicted. But until recently, we had no idea how things evolved earlier in the universe. And so the method we're going to use is called the close pair method, which is to find galaxies that are close in space and mass. The merger rate we can define as R, which is the number of galaxies, or number of mergers per number of galaxies per billion years. We can measure a fraction of those galaxies, which we call the pair fraction F. And then the rate is simply this fraction divided by a characteristic time scale. And so to go from a fraction to a rate, we just need to divide by this time scale, which we call the observability time of the galaxy merger. And that observability time has been calibrated using previous generations of simulations to be about 0.5 billion years or so. And so we can simply take observations of the number of galaxies in close pairs and convert directly to a merger rate using this equation and this calibration. A puzzle emerged with the installation of the Wide Field Camera 3 on the Hubble Space Telescope and other distant galaxy surveys. And that is once you push past about 10 billion years ago, the merger rates based on this technique flatten out. And so at this point, redshift 2, 10 billion years ago or so, there's a statistically significant discrepancy in the prediction from lambda CDM and the merger rate inferred using this close pair method as I've just described it. And so that posed a problem, because if there aren't really the number of mergers that our simulations are predicting, then we have a real problem with understanding how galaxies assembled. And so it's important that we rectify this situation. And so to answer this question, why aren't merging pairs more common, we decided to directly model the pair surveys with the same simulations that made the prediction in the first place. And so this work was started by an undergraduate intern I had at Space Telescope, Renato Guimarães, who spent 14 weeks at Space Telescope and MIT analyzing the Illustrious simulations. And what I asked Renato to do is to analyze real and mock deep fields, like this one I'm showing here. This is a deep field of simulated galaxies as it might be observed with the James Webb Space Telescope, and determine the best way of analyzing those simulated observations in context of the simulation in which they formed. And this led to a paper that involved Renato in 2017, where we're now taking these simulations and converting them directly into pair surveys of galaxies. And these surveys and example images are available at the link that I showed earlier, the Mikulski Archive for Space Telescopes. You can download 3 or 4 example fields like this one and play with the data yourselves if you wanted to. So what that allows us to do is make an apples-to-apples comparison with the real universe. And so this slide is showing a mock deep field from the Illustrious simulation compared with the actual Hubble Ultra Deep Field. On one side of the slide is the real universe, and on the other side is the simulated universe observed in the same units. And so does anyone want to wager a guess? Astronomers aren't allowed to answer the question. But does anyone else want to wager a guess as to which side is the real universe and which side is the Illustrious simulation?
The right side. I'm going to say left is real, just a guess.
Left is real, just a guess. Any other guesses?
Right side is real.
Right side is real. Why do you say that?
Just less galaxies, emptier space.
OK. Fair enough. Yeah, the right side is the real universe. The right side is the data from the Hubble Space Telescope. And the left side is our mock observations with Illustrious. But what you can see is that you notice there were some subtle differences in how the galaxies appear. But broadly speaking, galaxies have a similar distribution on the sky in our mock surveys as they do in the real universe, to within a factor of a few, a factor of 2, which is major progress in this game. And so we've taken now our mock surveys, gone and measured the pair fractions in the same way as observations, and recover the same trend. And so this is now our galaxy merger rate inferred from the close pair method as a function of time, showing the data, as well as our mock survey from the Illustrious simulation using the same technique that I described earlier.
A question.
Yeah.
About the last slide, it was obviously a difference in the total density.
Mm-hmm.
If you scale your Illustrious with the density, do you have some other numbers to compare the correlations quantitatively and see whether they're pretty close? What else do you do if you had scaled that?
So if you scaled it down to match the luminosities?
If you scale the densities to be the same artificially,
Uh-huh.
you're just knocking out a random sample.
The sizes would still be wrong. And
What
so
else would be wrong?
sizes. So one of the other problems with Illustrious galaxies is that they're too big. And so if you look at the distribution of points in this one, you see many tiny points of light on the right side and many more slightly puffier points of light on the left side.
What else?
Are
there some correlations?
That's a good question, and I am actually interested in making predictions like that, and I think we need to spend more time doing that. I don't know if there are very concrete ones that can be ruled out with data, but I hope there are. And so we've made our mock pair surveys and find the same results as the observers do. So that's good from one perspective, in that we think we have a model that seems to work, but we still don't understand why there's this discrepancy between the intrinsic galaxy merger rate measured in the simulation and the one we would observe using the close pair method, which is our tried and true method for understanding galaxy merger rates. And so the challenge is that this time scale that I've assumed from a calibrated set of simulations could be wrong. And so that's a pretty simple algebra explanation for why this could be wrong. And so if you just say, oh, actually our time scale is incorrect, we need to use a smaller time scale over here in the early universe, then you can have your data and your mock surveys agree with the intrinsic evolution of the galaxy merger rate. And so we wanted to look for a physical process that can account for that, and I think there's a very natural one. One is that that rapid growth of galaxies in the early universe means that distant pairs satisfy the selection criteria for close pairs for less time. And so here's an example of a galaxy from the early universe growing like gangbusters, because galaxies in the early universe are creating matter and forming stars at a higher rate than galaxies in the later universe, and the same selection cut at both times. And so the galaxy mass growth in the later example, before the galaxy merge, occupies a pair for more time. And so the maximum possible time that this pair could be observed is longer than the maximum possible time that this pair could be observed. And if you take a scaling like that one and apply it to our observability timescale calibration, you can bring your mock surveying data into agreement with the predictions from lambda CDM as the intrinsic merger rate. And so why aren't merging pairs more common? Well, rapid galaxy growth appears to shorten the observability of galaxy pairs in the early universe. And so our mock surveys imply that galaxy merger rate is indeed high in the early universe. I want to move now to how mergers might transform galaxies. So we need to move along our merger stages from the close pair stage to the final coalescence stage, where things are actually shaping the final galaxies we see. And I want to bring this back to the start of the talk by saying how studying distant galaxies can give us some insight into how our own galaxy came to be from the distant past to now. But it can also give us some insight about the distant future. And so those of you who see this small smudge of light here might know that that's another companion galaxy to the Milky Way called the Andromeda Galaxy, which is roughly the same size and mass of the Milky Way galaxy. And so we're actually in a close pair of galaxies, or a somewhat more distant pair of galaxies, that will eventually merge together. And scientists have now decided that this might occur 5 billion years from now or so. And so this is now those 6 merger stages from the perspective of life on Earth. And so we're going to be able to see the Andromeda Galaxy move closer over the next 4 billion years. It'll emerge as a brilliant transformation of the sky through the final coalescence of the galaxy. And so we can now use our observations of distant galaxy mergers to sort of understand how the future of our home is going to evolve in the distant future. So we return now to our mock image data set that I described earlier from Illustrious. We have tens of thousands of example mock observations. And we lose a lot of information about the mergers when we do this, as I mentioned earlier, through the process of observing them. And so we want to understand, how can we identify these distant mergers and their aftermaths in observations? Well, it turns out that our criteria for selecting mergers at these late stages of galaxy formation can select a pure sample of mergers. So we can be pretty confident that when we select galaxies based on their imaging, that we've got a selection of mergers. It's extremely incomplete. And so the standard criteria, so these are algorithms on the images that measure shapes and positions of clumps and things, find galaxies that are very obviously two nuclei or two things that are about to merge, but they might miss things that are more subtle. And so you may not even be able to see this plume of stars from this galaxy off to the right. And so if you have a massive elliptical galaxy, it's very, very difficult to tell if that galaxy recently experienced a merger just using observations alone. And so the approach we've taken is to treat our simulations and mock data as training sets for machine learning algorithms to try and overcome this problem. So to do that, we identify mergers in the simulation using a couple definitions. The one is that we have a 10-to-1 mass ratio between the galaxies, so they're similar in mass by a factor of 10. And they merge within plus or minus 250 million years from the mock observation. And so these are mergers that happen relatively nearby in time to when the fake galaxy is observed. And so that allows us to use a sample of labels of true positive galaxy, things that we know are galaxy mergers intrinsically from the simulation, and observe them and how they would be measured in the images, as well as galaxies which didn't have a merger in this time frame, and understand their differences. This is a very popular technique in the world and in astronomy. And so here's just an example of one other application of machine learning. This is showing pictures of cats and pictures of ice cream in different panels here. And so if you only had a few different parameters to measure from this image, you might be really confused as to which ones are cats and which ones are ice cream. So if you measure the total color or the distribution of color in terms of the shapes that the color occupies, you may never be able to separate cats from your ice cream or your owls from your apples if you only consider a few dimensions of those spaces. And so this is an application of neural networks, which I know a few of you in the department have been working on. That is one thing that people call machine learning, and one technique for classifying images from a set of labels. And the difference is that in this case, the labels have been put in by hand. So people have built a sample of things they call cats and said, yes, this is a cat, or said, yes, this is an owl, or this is an apple, using their eyes. Whereas now we have simulations where we can write down an algorithm to decide what's a merger, rather than using our eyes to decide what is a merger, or our measurements to decide what is a merger. We don't use the neural net approach in our group, but we use a related technique called random forest. And so the random forest technique is a group of random decision trees to subdivide space optimally for the training set. And this is work that had originally been led from observation space by Michael Peth, who was a JHU grad student, now working as a data scientist in Washington, D.C. And Michael used visually classified mergers, so labeled by humans, to select your training set. And then I was able to formally support Amanda Quirk as a space astronomy summer program at Space Telescope in 2016, where we took the results of Michael's code and software and converted it for use on our simulated pipelines of galaxy mergers and mock images. And Amanda's now a graduate student at the University of California, Santa Cruz. And so this diagram is just meant to give you an idea of the steps involved. We start with our galaxy training set. We divide it into a number of trees, and I'll describe what a tree looks like on the next few slides. But the main point is that after you have this set of decision trees, it's a way of taking a point in multidimensional space. So measurements of galaxies might involve measuring 15 different numbers about the light profile of a galaxy. And then for those 15 measurements, we get a probability that yes, the training set says that with some probability, 10% or 90%, that particular region of space is going to be a galaxy merger. And so the branches in this tree are defined as follows. We start with parameter 1, parameter 2, mergers in green, non-mergers in purple circles. And then we take a random selection of parameters. We choose parameter 2 by random. This is actually using a random number generator. We then take the sample of mergers and non-mergers from our training set and ask at what point in parameter 2, what space in parameter 2 best divides the data into mergers and non-mergers. And so this algorithm might choose in the first branch to put the dividing line here. And so it divides the sample in 2 distinct regions at this step. And then it only considers the rest of the space on this side down one path of the branch. And so the next step, it might randomly pick parameter 1. And then it takes the second branch and it asks from the remaining galaxies, what is the selection cut in the space of parameter 1, which best divides the sample into mergers and non-mergers. And from that, you get a selection in parameter space, and this can be many dimensions, a set of points that have a high probability of being galaxy mergers. And so this is one example where there happened to be a space where there's lots of galaxy mergers, and so our algorithm would come out with, yes, there's a 70% chance that a galaxy in this region would be a galaxy merger, according to our training set. We've taken this, applied it to our mock images and mergers, and cross-validated it. So this is now a plot of the completeness versus the false positive rate for our random forest classifier. And so a perfect classifier has a completeness of 1, false positive rate of 0. The classical techniques, the ones I showed you on the first slide of this section, achieve very poor completeness. And so they have something, they're better than random, but not much better than random. And so we're losing out on a lot of mergers using these techniques. Our new method improves in the completeness by a factor of about 2. And so we're able to identify a factor of 2 more mergers using this technique on our simulated data set. And so I think one of the nice things about this is that we've made a lot of progress, but I think there's also a lot of room to improve using better simulations, better training sets, better algorithms potentially for getting a better merger classification. But then how can we use this for data? So once we have a random forest classification tree, we can then apply it to data. So we measure the same parameters in our simulations and in our observations, and then we take those data points in multidimensional space and then push it through our random forest tree and to get a probability. And so this is now showing a plot of the galaxy merger rate versus cosmic time and showing the theory line. So the prediction for the merger rate is in black now. I've flipped the time axis from the previous ones. I'm sorry about that. But the purple triangles are from the pair technique, which I described earlier. And the black circles are now this simulation-trained machine learning classifier of real data from HST surveys, and showing general agreement, definitely an increase in the early universe, roughly the right order of magnitude of galaxy mergers. And so I think we're making progress at being able to understand how we can identify mergers with simulations and advanced statistical techniques. So that's the summary of the science results. I want to spend just a couple of minutes talking about where I'm going from here. And so the early mergers, even back beyond where we can probe now, might be crucial to form and transform the massive galaxies that form and evolve later. And so I'm really excited about the James Webb Space Telescope, which will be launched in 2019. It's a 6.5 meter satellite, telescope on a satellite, which will observe the universe from 1 to 30 microns of light. And it's really a multi-purpose, very sensitive instrument. And so we're going to get many different ways of probing this evolution. One is to actually characterize the mergers that we've identified in the first 3 or 4 billion years of the universe, but then also to measure mergers for the first time in the first 1 or 2 billion years of the evolution of the universe using the techniques that I've described. And the first proposals are now due on April 6th, which is really, really soon. And so I'm looking forward to all the great science that we're going to get out of this telescope. I'm part of what's called an early release science program for the James Webb Space Telescope called the Cosmic Evolution Early Release Survey, where the goals are to demonstrate efficient survey exploration of the early universe with James Webb. And the idea is to maximize the community science with James Webb. So it's only going to have a finite lifetime observing for us. And so we want to be able to very, very early on in the first observations. And so this team will have access, and my collaborators and I will have access to some of the earliest high-profile data on the distant universe from galaxies in this program. And so the thing I'm really interested in is simulations. And so here I'm now showing an example from the proposal showing this is the previous best we could do at these wavelengths that James Webb will observe from the Spitzer Space Telescope, and showing what we're expecting to see with James Webb. So just a massive improvement in the amount of detail that we can observe in galaxies. I'm collaborating on the next generation of big cosmological simulations. So the Illustrious project that I described today is a box roughly this size. Illustrious, the next generation, or TNG, is mostly complete and has a big team of collaborators trying to analyze the data. And so that has a simulation that has the same volume and same initial conditions as Illustrious 1, and that's shown here. But it also goes in other directions, so it goes to much bigger volumes in one example simulation. So this is a different simulation of a much bigger region of space, 3 times bigger on a side, so 27 times more volume. One of the biggest challenges with Illustrious is that we didn't have the highest density peaks sampled very well. We only had a few things that you might call a galaxy cluster, whereas Illustrious TNG will have dozens of things that you might call a galaxy cluster. And so really excited to analyze TNG in that fashion. And as we look even farther into the future, this is a plot showing the number of resolution elements versus year. I know this is probably hard to read, but this goes from 1995 on the bottom to 2015 on the right. And so this is the number of resolution elements in our cosmological simulations of galaxy formation that I described today, showing sort of a factor of 100 every 10 years growth over the past 2 decades. And if that continues, and we can use the techniques that I described today about mock observations, currently, we can fill a space using the technique of doing mock surveys about 0.3 square degrees, which is equivalent to basically all the deepest Hubble surveys we have today. In 10 years, we'll be able to fill a region that's 30 square degrees, which is roughly the amount of sky to be surveyed in so-called deep drilling fields with the next generation of ground-based and space-based telescopes. And then I'm participating in a couple aspects of the WFIRST project, which is the Wide Field Infrared Survey Telescope, which is planned to be the flagship mission launched after the James Webb Space Telescope in the mid-2020s, to try and best get at this data and simulations in the most efficient way possible. And so by 2038, after all the data from WFIRST have been taken, we'll be able to simulate the entire sky survey that WFIRST will be able to observe, which is quite an achievement and something I really look forward to. And the message I want to end with is that computing will be available to meet these needs. And so when I was really just getting started on this in my career, I was so worried that, we'll never be able to understand all of these things. There's never going to be enough resources. There's never going to be enough algorithms. Machine learning wasn't really a thing at that point. And so I figured we'd never be able to make progress. But the agencies and universities have really invested a lot in high-performance computing and scientific computing and algorithms needed to make progress on this challenge. And so I'm optimistic that, and I've seen calculations that yes, computing resources like storage and number of CPUs and algorithms will actually be available to meet these challenges. Thank you.
So we have time for some questions. Michael?
Would there be signatures apart from just the shape of galactic mergers? Like, would you see different metallicities in a merged galaxy?
Potentially, but I think our understanding of how metals evolve is even worse than our understanding of how other properties evolve, and so I think that's a long way away. There may be other signatures. I think a really compelling one is the velocities of information. And so with spectroscopy, we can measure Doppler shifts, so the relative motions of gas and galaxies. And so that could be a really interesting constraint. And I'm actually collaborating with a student who's writing a paper on that topic right now.
I had a question about your figure that was showing the rate of mergers versus time.
Uh-huh.
When you use this the random
This one?
What happens at 4 gigayears that introduces this very sharp jump?
I'm not entirely sure, but I think what might be happening is the shifting of the galaxy spectrum as it's redshifting. And so here I've measured it from particular filter bands, wavelengths of light. And so there might be a feature in the galaxy's shape of light that it just emits as a function of wavelength, which is coming in or out of one of those filters at that time. So I'm not 100% sure, though.
So I have a question about your, when you talked about the observability time scale,
Mhm.
scaled with galaxy growth, were you saying that if that galaxy were a little bit younger, it would simply be too faint to be in my survey? Because that's different from what I normally think of observability time scale for pairs, which is what I think of something like the dynamical time, or how long it'll take them to merge.
Yep.
That seemed to be a very different argument than what you were talking about.
Yes, so
I
it's
didn't quite understand the...
it's a different aspect, but I believe all of those, the two things that you just mentioned are both things that factor into the observability time. And so the observability time is both the time evolution of the merger in space. You have two gravitating masses, and they're going to evolve on some time scale. But you also have other things like this growth acting on them. And so in the late times in the universe, the growth time scale is going to be so long that it's actually then dominated by this dynamical time scale, which may be constant because the galaxy mergers might be the same in the early universe in terms of their mass budget, in terms of their gravitational evolution. They could be the same. I don't really know. But then that will then dominate at later times, whereas in early times, that time scale, dynamical time scale, is too long compared to the growth rate of galaxies.
So you just lose them beyond this. You lose them below the depths of the survey if you would observe them at a slightly earlier time.
Not exactly the depth of the survey, but the selection cut.
Okay, fine,
and so,
your selection.
Yeah, exactly. And so that's important for selecting the same galaxies as the simulation. And so it's important that we be able to put galaxies from the observations into a mass bin in order to test quantitatively how the simulation is doing.
I have one more question. John?
So we hear from various people that there's problems with cold dark matter that needs to interact more for galaxy formation. Some people propose absolutely enormous particle physics cross-sections.
Mm-hmm.
Why don't you have any of those problems in your simulation?
We do have those problems in our simulations. And so many of those problems happen on scales that we don't resolve here. And so we're actually not, if you went and measured the shapes of the dark matter halo profiles or the light profiles of low mass galaxies, you'd probably have a problem with some of these things.
But have you put in those sorts of parameters on these bigger scales to see if it makes any difference?
Personally, I haven't, no. But I think some of my collaborators are working in that direction.
Okay, that's great.
Thank you all.
Let's thank Greg again.